also related to noise. Just in general, often with devices, they generate some noise that is called thermal noise or Johnson noise. And it's literally comes as a result of thermal agitation of electrons. For example, a resistor, we say that has some thermal noise. So we can model a noisy resistor, and we'll model it as an ideal resistor in series with a noise generating voltage source. It turns out that the noise voltage is given by this expression. So R is whatever the resistance is. K is, we actually saw that with an antenna temperature. It's called Boltzmann's constant. That's also what we see with KT over Q that we run into with electronics. T is temperature in Kelvin, and then this delta F is the bandwidth measured in hertz. So that bandwidth is whatever bandwidth we're interested in. If, we're, say at our receiver, we end up looking at a specific bandwidth, then we only need to care about that particular bandwidth. So the maximum power transfer will happen when we connect a matching resistor to this resistor that is in series with this noise source. And it turns out that the power then is just this. The resistance drops out and we're left with KT times the bandwidth. So this works for resistors, but oftentimes other devices, like antennas, will be told a noise temperature. And it's confusing because you think that noise temperature would have something to do with the ambient temperature or the actual temperature. For resistors, that is the case. For resistors, this temperature is just the ambient temperature. But for other devices, we can be given a noise temperature, and if we want to find the noise power that is creating, we just substitute that in this equation for T.